Hi. I'd like to clarify that my wife is an artist and I'm a wannabe artist. So I know mathematics and I know how to write computer programs to generate cool shapes. So it's sort of like art, but anyway, that's what I want to talk about. So my name is Doug Moen. I'm an aspiring digital artist, and I make 3D printed art using open source software, which I wrote. The program is called Curv. And today I'm going to explain what creative coding is. I'm going to show you my process, and I'm going to explain why I wrote Curv. And on the screen, those are a couple of 3D printed objects that I created using Curv. So creative coding is the act of writing a computer program to make art. It's fun, it's interesting, and it lets you do things that are hard to do in any other artistic medium. To start with, creative coding is a fun and rewarding way to learn computer programming. So you can write simple programs, you get immediate visual feedback, and you don't have to worry so much about bugs because you can still get interesting results. And if you go deeper, you can find communities of creative coders on the internet who share their codes and ideas, so you can make new projects by building on other people's work. And some groups are competitive when people try to make short, beautiful programs that produce amazing looking results. And then the program itself becomes part of the art, which is good news if you're a computer programmer who wants to be an artist. And that's actually, on the screen, that's a little program in Curv that I wrote last year. And that is 3D printable. You just have to select which animation frame you want to print. So 3D printers are cool, but they're even cooler if you can design and print your own art. So I use creative coding to make abstract geometric art, and this is something that you can do too, even if you don't have conventional artistic skills. So this would be called generative art. The idea is that you write a computer program that generates a picture for you, instead of drawing it yourself with oil paint or whatever. The advantage is that the computer can generate imagery that's way more complex and precise than anything that you could easily do by hand. And if you add numeric parameters to this that control what gets generated, then we call that parametric design. By tweaking the parameters, you can explore a range of possible designs and find the one that best expresses your artistic goals or just looks the coolest. So the Curv project started a couple years ago. I played with a number of different creative coding platforms. The two that impressed me the most were OpenSCAD and ShaderToy. So on the top part of the screen, that is the OpenSCAD user interface. You make blocky looking 3D objects made out of polygons. The language is really nice though. It has all these high level concepts in it like cube and sphere and intersection and so forth. I found the language really easy to get into and really addictive. But I ran into a brick wall, and it's oriented towards 3D printing. Everything you make is 3D printable. But the problem with OpenSCAD is I ran into a brick wall when I tried to make curved, organic-looking shapes and fractals. So then I found ShaderToy. It's a website. It's really great for making awesome-looking organic shapes and fractals, and that's actually an animation frame of a fractal mountainscape with so it's just super powerful in terms of what you can make it do visually. But it doesn't do 3D printing. You can only make demo videos with it. And the programming model is really low level and complicated. It took me months to figure out how to write a ShaderToy program. So that's when I decided to create my own language. So Curv combines the best features of OpenSCAD and ShaderToy. So like OpenSCAD, it has a simple, expressive, and easy-to-use language, but it's built on top of shader toy technology, which makes it very powerful. So, so the Curv language has two programming interfaces. So on the left, there is a program that just says Sphere 1. So that's the high-level interface. It's made out of building blocks, high-level building blocks. It's a library of standard geometric shapes and operators for transforming and combining these shapes. These can be plugged together like Lego to make 2D and 3D models. It's inspired by, that part of it is inspired by OpenSCAD. And then on the right side of the screen, that's actually a definition of the sphere building block, also written in Curv, and that part of it is the low-level interface. That's the part that is inspired by shader toy, and it you define shapes and colors. You define shapes using signed distance fields, which I'll mention again later. So next I want to do a live demo. So yeah, so basically I'm going to do some creative coding using Curv building blocks. So when you start writing Curv, the first program you should type is the program box. So basically that's the entire program. You just type the word box and you get a box. So that's pretty easy. Now, next thing we're going to do is we're going to change the size of the box by specifying X, Y, and Z dimensions. So I'm actually going to pass an argument to box, and then we will get that. So it's 5 units high along the Z-axis. And so Curv has many transformations that modify a shape. So examples are move, rotate, scale, stretch, bend, twist, and color. In this demo, I'm going to transform the box into something interesting using a chain of transformations, which is similar to a pipeline in the Unix shell, if you know Bash. So first let's change the color. So I'm going to change the color to red. And so what I've done here is I've created a pipeline. So we take a box, and then we pipe it into a transformation. In this case, the transformation is color red, and then the output of that is a red box. So next thing I'm going to do is I'm going to make the color into a parameter that we can manipulate using a color picker. So the parameter is called C, and the initial value is, well, I'll make the initial value green just to, so something happens on the screen. And now I got to replace the word red with the variable C, and there we go. We have a, so there's the color picker. So I can just, mess around and change it to my favorite color, which is, cyan or whatever. So I don't know, there I just, so now we're doing parametric design, right? Because I've got a parameter and I just tweaked it. So that's parametric design. So next thing we're going to do is we're going to deform the box using some additional transformations. So I'm going to twist it, and twisting is extremely cool. So I'm going to twist it 90 degrees divided by 5. So the argument to twist is the angle of twisting per unit of distance traveled along the z-axis. So this box is 5 units high along the z-axis. So what this is going to do is it's going to twist at 90 degrees. And there we go. And so then next thing I'm going to do, well, we're going to add another parameter, of course. So I'm going to make another parameter called angle, and it's going to be a slider, and the number is going to vary from 0 to 720 degrees, and initial value is 90. And again, I have to change that, change the 90 into the angle parameter, and now I've got another slider. So now I can mess around with the slider. And look how smooth the animation is. Isn't that nice? Yeah. Thank you very much. I was very excited the first time I did this. Um, so, oh, yeah, well, in just a minute I will. So then you just have to wait, 2 more transformations. So then the next move, I'm going to rotate the object so that it's lying along the x-axis. And this is to get it into the correct position for the final transformation. So, okay, so I want to, I'm going to show the axes so that it makes sense what I'm doing here. So, okay, so now I have, okay, red is x-axis, green is the y-axis, and blue is the z-axis. So it's right now it's aligned with the z-axis, and I want to align it with the x-axis, which is red. So to do that, I have to rotate it around the y-axis, which is green. So I'm going to do a rotation right now. Rotate, angle, 90 degrees, axis, y, y-axis. And there it is. So it's rotated, and it's ready to... So the final transformation that I'm going to show you is the bend transformation. What this does is it bends it around into a ring. And I don't need any arguments because the default arguments are perfect for what I want to do. So there it is. And I'll get rid of the axis display because we don't need it anymore. Just comment it out. And so there's the shape. And then now I'll mess around with the slider again. That's it. I'm not finished yet. Yeah. But wait, there's more. Okay. So there's a lot more things that Curv will do. And I don't have time for that in the demo. But you can make, there's operators that make curved organic looking shapes. There are procedurally generated textures like the wood grain on that thing on the left. You can make fractals, and you can make 2-dimensional models, and you can explore the Mandelbrot set. There's a lot of depth there in the program. So I want to finish up by talking about how Curv works. Okay, this is the technical part of the talk. So I said earlier that Curv is built on shader toy technology, which makes it powerful. Curv represents shapes using mathematical functions. The geometry of a shape is represented by a distance function, which maps a point onto the distance to the nearest boundary. It's positive if you're outside the shape, 0 if you're on the boundary, and negative if you're inside. So Google signed distance field if you want more information. The color of a shape is represented by a color function, which maps points onto colors. In the future, we will extend this representation to support advanced 3D printing. We'll add an alpha component to colors to represent translucency, and we'll add a material function so that you can continuously vary the material from one point in the interior of the model to another. And because there are printers that are capable of doing that, you can't really do that very well with triangle meshes, which is what the industry uses. But you can do with continuous functions. You can do this. So function representation is very powerful. Shapes can be infinitely detailed. They can be infinitely large. There's a wide range of shapes and color patterns that can be described exactly using mathematics instead of an approximation like a voxel grid or a triangle mesh. And distance, if you're interested in fractals, distance functions are the preferred representation for fractals. They're really the only representation that supports deep zooms into 3D fractals in real time. Function representation can be directly executed on the GPU, and this is how Curv renders shapes in animations, and that's why that animation was so smooth. So let's say maybe you'd like to get more involved in creative coding. Well, there's a number of different communities and software projects that you could check out. So the one everybody's heard of is processing.org. So that has, basically, it's the oldest creative coding, live coding platform. It has a very large community. It's very popular. You can do a wide range of things with it. It's general purpose. You can do 3D printing, but I don't recommend it. It's not really the main focus. If you want to do 3D printing, OpenSCAD.org is a much better choice. It's got that high-level building block programming interface that inspired Curv, and it also has a live, vibrant community. Mandelbulber.org is a software tool for making fractals. It's a product of the Fractal Forums online community, and they've done a lot of groundbreaking research on creating 3D fractals using signed distance fields. The demo scene is an international subculture of creative coders who create demos, which are self-contained programs that generate audio and video. They hold festivals and competitions all over the world. Shadertoy.com is a website for coding, running, and sharing demos that are written using GPU shader programs and signed distance fields. And finally, there's my project, Curv. Our website is curv3d.org, and it's on GitHub under Curv3D. And Curv is a young project with a small community of early adopters. And we hope that 2019 will be a big year for Curv as we move towards a 1.0 release of the software. Thank you very much.